With this lecture, we begin our study of angular momentum, which is the same as the study of the orthogonal group in 3 dimensions, or equivalently, the simple unitary group in 2 dimensions, as we will show later in the course. This is the study of angular momentum. We are familiar with angular momentum from our earlier courses in physics, where the angular momentum vector L is defined as the radius vector r cross p for a given particle. Obviously, if we have a large number of particles, then we take the total angular momentum vector as the sum over I of each vector ri crossed with the pi for that particular mass. We can define more generally an angular momentum in terms of, rather than using the cross product, we can define an Lij as xipj minus xjpi, where I and j go 1, 2, and 3. The origin of the connection between the two of them is that Li is epsilon ijk xjpk, and that relates the Lij as defined between the x and the p's to an Li. The reason that the cross product is not the preferable way to define the angular momentum is because the epsilon symbol, epsilon ijk, only has this character in 3-dimensional space. We can define and use this form in any dimensional space and end up with a tensor of the appropriate rank. However, it's only in 3 dimensions that the cross product exists, because the epsilon symbol in 3 dimensions has 3 indices. Therefore, the contraction of 2 of those indices with vectors leaves you with 1 index, which is an object which transforms as a vector. But in 4 dimensions, 5 dimensions, and other numbers of dimensions, one cannot make that type of definition. So, although this is a nice and useful way to think about it, where angular momentum is a vector, it is much preferable, or this method here, it's much preferable to think of angular momentum as a second-rank tensor. Of course, we make the connection that the x component of L, or using a capital L, its x component, is actually equal to L23. So Lx is equal to L23, Ly is equal to L31, and so forth with the circular rotation of the indices. Now we can find the commutation rules between the angular momenta using our commutation rules between x and p. Using the fact that the xp commutator is IH bar, we can do the following derivation. We're going to take the commutator between L2 and L3. Therefore, we take the commutator of x2, this is L2, x3p1 minus x1p3, commuted with this operator, L3, which is x1p2 minus x2p1. Now, in order to take that commutator, we must take all 4 products going this way, and then that will give us this term here, then the negative of those going in the opposite direction. So working through those, we can see that we begin with x3p1, this one, times x1p2. And next we take minus x1p3 times x1p2. Now we've taken both terms times this. We now take both of the terms times the second term. So we have x3p1 times x2p1, and that of course has a minus sign from right here. And then finally x1p3 times x2p1, and that of course has 2 minus signs, which gives us a plus sign. Likewise, taking those products in the opposite order, we have these 2 terms times these 2 terms, which gives us this product right here, which is easy to work out for the reader. Now, we will notice that these 2 middle terms are the same in the upper and the lower, except for their sign. For example, this is x1 and an x1. The P2 can be moved all the way through because it commutes with both x1 and P3. And the P3 can be replaced over here. So this term and this term are exactly the same, or can be put in exactly the same form by moving the P2 and the P3 and interchanging them, as both of them commute with x1. That means this term cancels with this term. Likewise, we can take the x2 and x3 and commute those both through P1 and get the lower term here, and therefore it follows that this term and this term are the same except for the sign, and therefore they cancel. We are left then with two terms that do not cancel, the first term and the last term. The first term, one will see, can be put in the form of this term right here. x3 times a P2 with a P1x1 in the middle. And now we want to take the second term, which has a negative sign, and put the x3 first, which we can do because x3 commutes with both of these, and put the P2 last, which we can do because P2 commutes with both of these. And then we end up with an x1 P1 product in the middle. We did that because then that shows us very explicitly that both of these terms are of the form x3 on the front, and the end will be a P2, and in the middle we have P1 x1, x1 P1 with a negative sign. Well, that is nothing but the negative of this commutator, because if we look at this commutator right here, then we can see that xp minus px is equal to IH bar, and here we have the opposite form, so that would be a minus IH bar times x3 P2. And we would get this term right here by actually forming that commutator. Likewise, we get the same result over here. We have P3 and an x2 here, and we can put these in the following form. We have the P3 first, the x2 last, and we have x1 P1 minus P1 x1 in the opposite order. But xp minus px is IH bar, so we get a positive IH bar times P3 x2. And that will be exactly the same as xp minus px is going to be IH bar. So we have an xp minus px, which is going to give us an IH bar with a P3 and an x2, P3 and x2, and an IH bar. We have reversed the order on the P3 and x2 because they both commute with each other, but that term P3x2 or x2P3 has a positive sign because of the commutator of xp. That leaves us with the result that the commutator of L2 and L3 is equal to IH bar x2P3 minus x3P2. But this is the term L1. Recall that L1 is x2P3 minus x3P2 in cyclic order, and therefore we have proved that the commutator of L2 with L3 is IH bar L1. Likewise, one can show that L1 L2 is IH bar L3, and L3 L1 is IH bar L2. And the order is 1, 2, 3 in cyclic order, 1, 2, 3 in a cyclic order, 1, 2, 3 in a cyclic order. And whether we write these in the form of a single index or a double index is now our option, depending upon what would be clearer under the circumstances. We know that although these operators are defined originally in terms of x and p, after determining the structure constants, we can treat this as an actual Lie algebra. And this is a very critical point that we want to emphasize, is by starting with the x and p's and knowing their commutation rules, and then having an unambiguous definition of other operators in terms of position and momenta, we can find the representation of the commutation of these operators, whatever they might be, whatever functions. And here we've got angular momentum, we could find other functions. And then if that set closes, that can then be thought of as a new type of Lie algebra that rests upon the previous Lie algebra. On a deeper level, we're actually defining new Lie algebras based upon position and the derivative with respect to position, which is of course the momentum. These are basically forms that we're studying, and so we're studying forms dependent upon or functions of derivatives and variables. We continue with our work on the O3 Lie algebra. We also need to compute some other relationships. We need the commutator between Lij and xk and Lij and pk. Now this is straightforward to work out. We simply take Lij with xk and write it in its expanded form. Here we only have to take the commutators of these various components with these components here. Of course, the x's commute with the x, and if we expand this product, we're left with the following form. xipj times xk minus xjpi times xk, where we've taken the two terms like this here, from the left-hand side. Then from the right-hand side, we have the negative of xk right here, where xk multiplies the other two, xipj, and xk then multiplies with a positive sign because we've inverted the commutator and we get another negative sign from this, which gives us xk times xjpi. We're now going to use the fact that pjxk is equal to xkpj minus ih bar delta jk. And when we use that in the following, we can do the following expansion. Likewise, we will use pi xk is xkpi minus ih bar delta ik. And we do this on the left terms. And when we do that, we of course are able to change the px here into an xp. And this px right here interchanges with an xp. Upon completing that, we see that we have taken this term, and by performing this substitution right here, the first part, xi times xkpj, becomes exactly the same as the second term with a minus sign, and so those two cancel, leaving us only a minus ih bar delta jk times the first xi, minus ih bar delta jk times xi. Likewise, when we take the second term here and perform this substitution, we get the p and the x interchanged, making it identical to this term but with the opposite sign, so this and this will cancel, and it leaves only the second term, which is minus xj times a minus ih bar delta ik. The two minuses cancel, and we're left with minus ih bar delta ik xj. Now we can rewrite that and change the signs in the following way. We want to put the we want to interchange the x and the l, and when we do that, we change all of these signs, and so we can write the commutator of xk with Lij is equal to ih bar, which we pull out front, times delta jk xi minus delta ik xj. One can also show, because of the exact symmetry between x and p, very quickly that the commutator of pk with Lij is exactly the same form. Now, we point out here that the way to remember this is if you put the Lij in the second position, then the indices that are carried on the x, which is the only thing left on the right-hand side, first is the I here, and second is the j, and the j has the negative sign. The other two indices, since you have xi, you must have two more indices k and j, and here's the delta kj, which you can either write delta kj or delta jk, it doesn't matter. And likewise for the other two remaining indices here. Likewise, we see exactly that same form right here. In general, if we have an object, a sub k, it is a vector under O3 if and only if ak commuted with Lij is equal to IH bar times AI and AJ with the delta functions in front in exactly the same forms as the x's and the p's. Therefore, this commutation relationship is saying something much deeper than we see at first. It says that x and p are simply vectors under the rotation group. And they are, these components are going to transform as the coordinates do. And of course we know that pk does, and anything that's going to transform as the coordinates will have the same commutation rules with Lij. When we become more familiar with the Lie groups, we see that the commutator of the generator of the Lie group with an object defines, of course, how that object will behave under the group generated by that infinitesimal transformation. So we can see here that x sub k and p sub k are vectors under O3. Now moving on from that, if we have an object S such that S with Lij is equal to 0, then we say S is a scalar under O3. If we have an object T such that it has multiple indices, L, M, N, and so forth, if this object has the commutator that is the same as the product of A sub L, A sub M, A sub N, and so forth with exactly the same indices, then we say that T, L, M, N is a tensor of that particular rank, namely however many of these indices we have under O3. I want to emphasize again the great importance of this, because what we're saying normally is we define an object, a scalar, a vector, or a tensor, if it has definite transformation properties under the group. In particular, if we have a rotational transformation, we say A sub k, or vector A, is a vector if it transforms exactly like the coordinates. And of course, momentum being a vector does transform exactly like the coordinates. Here we're seeing then, I'll repeat, a deeper origin of that, saying that if the commutator with the Lie algebra, which generates that, is in fact the same as the coordinates, then in fact we will have the object which is a vector. So the nature of a vector, a scalar, or a tensor of any rank is defined by the commutation rules with the transformation generator, or that is the Lie algebra. Now, the reason that that can be of some power is the fact that you could have, for example, a very complex group, and it could have a rotation part, a Lorentz transformation part, a dilatation part, and under these different parts, an object can transform in different ways. So you can have an object that is a scalar under one thing and a vector under something else. And that is, of course, just defined by that particular commutation rule with that particular Lie algebra, which is a subalgebra of the larger algebra. We're now going to take the algebra, the Lie algebra 03, and look at its Cartan subalgebra. We're going to write this algebra in a form that is familiar to us from the Cartan decomposition. Mainly, we're going to find a maximum commuting set of operators. We're going to find the Casimir operators, and we're also going to find operators which remain after the Cartan subalgebra is removed, which are, as will turn out, the raising and lowering operators, or the E operators as we previously defined them. In order to kind of abstract from what we've previously done, we're now going to call this LieAlgebra a set of J's rather than a set of L's. The implication here is that the J is the total angular momenta, and it stands on its own. And there are three of these: Jx, Jy, Jz, or J1, J2, and J3. And we define Jx, Jy as IH bar Jz with cyclic permutations. It's very easy to check from that simple commutation rule that each of the J's will commute with J squared, where our J squared is Jx squared plus Jy squared plus Jz squared. And that is, by definition, giving us our total J squared. One can intuitively understand that commutation rule rather easily. J squared is a vector dotted with itself, and the dot product of a vector with itself has a length which is invariant under the rotation group. Therefore, even though these are generators which generate the rotation group itself, here we have a length, and that length is, of course, to be invariant under its own under the rotations that it itself generates by its components. So it makes sense that Jx squared plus Jy squared plus Jc squared, as the length of the angular momentum vector, is invariant under its own group generated by the Jx, Jy, and Jz. Consequently, we can see that J squared is a Casimir operator of O3. It turns out that there's no other function of Jx and Jy and Jz that's nonlinear that is independent of J squared functionally, and that gives us new information. So there's only one such Casimir operator. We now want to look at the Cartan subalgebra. Cartan subalgebra can be really any one of the J's, but we can only take one of them. We could take Jz, we could take Jx, we could take Jy. Traditionally, we take the angular momentum in the Z component to be the Cartan subalgebra. And there's only one element. How do we know that? Because it's very simple to show that any linear combination, alpha times Jx plus beta times Jy, commuted with Jz, if we require that that commutator vanish, it follows that alpha and beta both must vanish, and therefore there is no other linear operator that is going to commute with Jz. We now define two other operators rather than using, we're going to have our Cartan algebra Jz, which is going to be our H operator as we previously used, and we now need to find other operators that are left in the algebra, which are of course Jx and Jy. But rather than use Jx and Jy, we're going to define two new operators, J plus, which is Jx plus Ij, and J minus, which is Jx minus Ij. We'll notice that each of these is the dagger of the other operator.